Now, here comes one of the most important theorems that we are going to learn in graph theory here, which is called Menger's theorem. Okay? So, at the end of this lecture, you will see that this theorem is equivalent to many important theorems in combinatorics. In fact, at least 7 of them we will list today, right? And each of the 7 theorems are basically equivalent to each other, right? So basically, if you prove one of them, from that, assuming that, you can prove the others easily, right? That's the idea. Okay? So they are kind of equivalent results. And this is very important theorem. This is called Menger's theorem of connectivity. Okay, so here is the statement of the theorem. So let U and V be non-adjacent vertices in the graph G. Then the minimum number of vertices that separate U and V is equal to the maximum number of internally disjoint UV paths in the graph. Okay. So the theorem says that there is a close connection between the separating sets, right, its cardinality, and the internally vertex disjoint paths. Okay. So if you talk about UV paths, then the minimum number of vertices that can separate U and V, right? So you take U and V, look at all the paths, and find a subset of vertices which will disconnect U and V, right? So if you remove these vertices, then the graph will be, there is no UV path in the remaining graph. Then it's a separator. Find the minimum cardinality separator, right? That minimum separating set is actually equal to the maximum number of internally disjoint UV paths in G. Okay. And one direction you should be able to see very clearly, right? Because if every path is going to use the separating set vertices, right? Then it can use at most, right? At most one. You just use at least one vertex from the separating set to go from U to V. So you definitely cannot have more than these many disjoint paths, right? Internally disjoint paths. That is clear, right? Because every path contains one of these vertices, and therefore each path have at least one. Of course, you can have more, maybe, right? But then you cannot have more than the minimum separating set, that many disjoint paths. So that is clear. But what is not immediately clear is that why there should always be that many internally disjoint UV paths. Okay, so this is what we are going to prove today. Okay, and the proof is also very interesting, so you should pay attention to it. Okay, so there could be there are several proofs. We are going to give a specific proof by induction on the number of edges. So let the graph contain m edges. Okay, so G is the graph; it has m edges, and if m is equal to 0, then this holds trivially, right? Because there is no edge, so there is no UV paths. We are non-adjacent vertices. There is no UV paths, and m is also 0, so there is no separating set is also empty set, right? The empty set separates because there is no paths. So therefore, the result is trivially true. So therefore, now we can assume. So this is the base case. So we can assume, the result holds for graphs with size strictly less than m, where m is at least 1. Right? Now let G be a graph of size m, right? Now, without loss of generality, we can assume U and V are to be in the same component. Why is this? Because if U and V are in different components, then there is no UV paths, and you don't need any vertex to separate U and V because they are already separated, right? So that is empty set again, and therefore we can assume that U and V belong to the same component. So we assume that the graph has size m, and we have this graph, and U and V belong to the same component in the graph. Now we can assume something further, right? If you have a minimum UV separating set having, let's say k at least one vertices, right? Because 0 is already done, right? Then definitely G has at most k internally disjoint UV paths, as this is we mentioned before, right? Because every path must use at least one of the vertices, so it cannot have more than k IVD paths, right? So what remains to prove is to show that we can actually find k such paths, right? Now, if k is equal to 1, again the result is immediate, because if k is equal to 1, what it says is that the graph has a cut vertex, right? I mean, there is a cut vertex between u and v, right? U and v can be separated by a single vertex, means that there is a cut vertex that separates u and v. Now, if there is a cut vertex between u and v, then every path must go through that vertex, right? So, since every path must go through that vertex, you cannot have more than one disjoint path. But because the u and v are connected, there is at least one path. So therefore, we get one path, and that is the maximum that we can have, right? So therefore, that also holds, right? So k is equal to 1 is also immediate. So without loss of generality, we assume that k is at least 2, right? Because we have done it. So we will assume that k is at least 2 for the remaining part of the proof. Okay. So we define, we divide the proof into three cases. Okay. So the definition of these cases are very interesting because it makes the proof very easy. Okay. So let us see how we define this case. Okay. So the first assumption is that, right, you have this component in which you have u and v are connected, right? And you have a separating set, let's say x in the graph T. Okay. Now, the assumption is that for some separating set of the minimum cardinality, okay, so x is a minimum separating set for the for u and v, and for at least one of these separating sets, right? So at least one of the separating sets, minimum separating set, has a property that there is a vertex, right, which is adjacent to u as well as v. Okay. So the assumption is that there is some minimum separating set where a vertex in the set is adjacent to both u and v. Okay. So there is an edge from u to x and also an edge from x to v. Okay. So if this happens in the graph, right? This is the first case, right? Suppose there is such a minimum separating set. In that case, what we do is the following. Okay. So what we do is we remove the graph x from the graph G, and you look at the graph G minus x. Okay. So look at the graph G minus x. So in G minus x, of course, this edges, right, u to x and x to v will also go, right? And then you get a smaller graph, right, with less number of edges. And in this graph, we can see that x minus the vertex x is a separating set for u and v, right? Because once you remove, the entire set x, u and v are disconnected. I can do this in two steps, right? I first remove the vertex x and then remove the remaining vertices in x, right? So therefore, x minus singleton x is a minimum cardinality UV separating set in the graph G minus x, right? Because if there is even a smaller one, I can remove that and remove x so that it gets separated. So therefore, we will assume that that is not the case. Therefore, it is not the case. So therefore, x minus singleton x is a minimum cardinality UV separating set in the graph G minus x. But the point is that if G minus x has at least two edges less, right? So I can use induction because the number of edges is less. And I am inducting on the size of the graph, which is the number of edges, right? So if the size of G minus x is strictly less than m, right? This implies that we can use induction hypothesis. So what is the induction hypothesis? Right? If if the number of edges is strictly less, then no, the result holds. That means that you can find k minus 1, right? So this was cardinality k, right? Then you can find k minus 1 internally vertex disjoint UV paths from U to V in the graph G minus X. Okay? So in the graph G minus X, we can find internally vertex disjoint UV paths from U to V, right? There are k minus 1 such paths. So once you get this many paths by induction, what you do is to just add the path U to X, X to V, right? Because U and V are adjacent to X. So UXV is a path which was not present in the graph G minus X. Right? So therefore, this path is going to be internally vertex disjoint from all other paths, right? From the all other paths that we got obtained by the induction hypothesis. So adding this path, I get k minus 1 plus 1, there is k paths. So I get k paths in the graph, which solves the case for this case, right? So this case is okay, right? So if the graph contains a separating set with the property that one vertex is adjacent to both U and V, then we can easily use induction, right? Okay, so that is the case 1. Okay? So once we finish with this case 1, we will assume case 2 has the following structure. Okay. So in this case, we assume that for every minimum UV separating set in the graph G, okay, for every minimum UV separating set in the graph G, either every vertex in the set S, let's say the separating set S, is adjacent to U and not to V. Okay, because if there is one which is adjacent to both U and V, then we are in the previous case, right? So we will assume that every minimum UV separating set has a property that, right, all its vertices are either adjacent to U, right, but none of the vertices are adjacent to V, or all the vertices are adjacent to V and none of them are adjacent to U, right? So every separating set, minimum separating set has this property, right? This is the second case, right? Maybe this doesn't happen, but we will assume that suppose this happens. If one of these cases happens. So what can we see from this structure, right? So if every vertex in the separating set is adjacent to U, but none of them are adjacent to V, then the UV path, of course, goes through the vertex at S, right? So every UV path goes to a vertex in S. Then from there, it has to take some path to V, right? But since there is no direct edge, there is at least one vertex in between when I go from S to V, right? So S to V, we should contain at least one vertex. So which means that, the length of the shortest UV path, right, from U to V, let's say, right, must contain at least 3 edges, right? Because U to S, I should need one edge. S to V, I need at least 2 edges, right? So the length of the shortest UV path, which is the distance between U and V, is at least 3, right? Because every path must go through S and then some, right, path of length 2 from S to V, right? So distance is at least 3. So we will observe that if the case 2 happens, then the distance between U and V is at least 3. Okay? Now what we are going to do is the following. Okay? So since you know that there is a path of length at least 3, we will take such a path, okay, such a shortest path. So you take a shortest UV path, right? Whatever is the shortest, it can be 3, it can be 4, whatever it is, but the shortest one that you can find in the graph from U to V, right? Whatever path that you can find. So consider P to be the shortest UV path, right? So it starts from U, go to some vertex X in the set S, right, the separating set. Then from X it goes to an immediate neighbor Y, which is not the vertex V, of course, because there is no direct edge from X to V. And then from Y, there is some path to V, right? It could be an edge or a longer path. So you have the shortest path, which goes from U to X, X to Y, and Y to V. Now, XY is an edge because that is how we take the define the vertex Y, right? So the edge E is equal to XY. Now what we do is that in this graph, I remove the edge E. I don't remove the vertices. I just remove the edge E. Okay. So suppose you have something like this. So let me draw it for you. Right. So you have U, then you have some vertex small x, let's say in the set S, and then some Y, and then some path to the vertex V, right? So you have this Ux, xy. So I am going to remove basically this edge xy. So the xy edge is removed in the graph. Of course, the other edges, whatever is there, are going to be present, right? Whatever it is, are going to be there. I just removed the edge xy. Now, once I remove the edge xy, what happens to the minimum UV separating set, right? See, I know that S is a minimum separating set, which means that removing the vertices of S will make the graph disconnected, and that is the smallest set, right? Now in this, if I remove one of the vertices, right? If S has k vertices and I remove the vertex X, of course I know that the remaining set has k minus 1 cardinality, right? But if I remove X, of course, I also remove the edge xy, right? Because X is a vertex incident to the edge xy. Right? So therefore, removing the edge xy, removing the vertex X will also remove xy. So if I remove only the edge xy, right, the number of the minimum separating set cannot decrease by more than 1. That's what I wanted to say, right? Because just removing x itself will remove xy. So in G minus xy, the minimum cardinality UV separating set cannot be less than k minus 1, right? Because I can just remove x, which will remove, it's a subgraph of G minus xy, and then that has separating set size actually equal to k minus 1, right? Now, the claim is that, of course, in a typical case, once you remove an edge, it can also decrease the cardinality of the separating set. But we are going to say that in this particular case, it will not decrease, right? The minimum separating set in G minus xy is actually again has cardinality equal to k. So we are going to prove this, but I want you to think about why in G minus xy you cannot have a separating set of size k minus 1. Okay? So think and try to prove it yourself. If we are in case 2, that every minimum UV separating set in S, set G, set S in G has either all the vertices in S are adjacent to U and not adjacent to V, or all the vertices are adjacent to V and not adjacent to U. In this particular case, if I remove this edge xy, right, in the shortest UV path, the edge xy, then it cannot decrease the separating set cardinality of the separating set. Okay. So think about this. So how do we prove this? Okay. Suppose, for the contrary, suppose that there is a k minus 1 element separating set in the graph G minus E. Okay. So we assume that there is such a separating set in G minus E. So we call the set as let's say Z, which is equal to Z1, Z2, Z3, etc. Zk minus 1. Okay, so we have a k minus 1 element separating set, we assume, in the graph G minus E. Now, what we know is that Z union X is a separating set, a UV separating set for the graph G, right? Because, right, once you remove X, G minus, you get a subgraph of G minus XY. So if I remove all the elements of Z, then you get a separating set in the graph G, right? Because this is the separating set in G minus XY, and G minus X, right? For example, let me just write it, right? G minus X is a subgraph of G minus the edge XY, right? Now, since Z is a UV separator for G minus XY, it is also a separator for G minus X, right? Because it's a small subgraph. So, but now we know that the minimum cardinality of a separating set is K in the graph. So I have removed one vertex, which is X, right? And then I have removed one vertex X, and then I have removed the K minus 1 vertices in Z. So therefore, it has cardinality K. So therefore, it is a minimum separating set also, right? So Z union X is a minimum UV separating set in the graph G. But we know that by the definition of X, right, with the choice of X is adjacent to U, right, but not adjacent to V, right? So that was our assumption, right? X is basically adjacent to U, right? And of course, because of the property of S, it is definitely not adjacent to V. Now, X is adjacent to U and not to V. Each of the Zi's must also be adjacent to U, right? Because Z union X is a minimum separating set, and we assume that in the case every vertex in the separating set is either adjacent to U and not to V, or adjacent to V and not to U. But one of them is already adjacent to U, therefore everything else must be also adjacent to U, right? So therefore Z1 to Zk minus 1 is also adjacent to U, right? But not adjacent to V, right? Now this we can do because we assume that K is at least 2, right? Because K is at least 2, right? K is, we assume that K is at least 2, right? Because when K is at least 2, we don't fall to the induction trap, right? We know that this set is non-empty, right? This set Z1 to Zk minus 1 is non-empty, and therefore we can do the following. Okay, so if I look at Z union Y, right? This Z union Y is also a UV separating set, because once I remove Y, again I remove the edge XY. So G minus Y, right? As we just noted earlier, G minus X, similarly G minus Y, is also a subgraph of G minus XY. Now, because this is a subgraph of G minus XY, right? If I remove Z1 to Zk minus 1, which is a separating set for G minus XY, then I get a UV separator for the graph G also, right? So therefore, we see that Z union Y is also a separating set for the graph G, right? Now, if Z union Y is a separating set, now Zi is are adjacent to U because Y is adjacent to Zi's are adjacent to U because we proved it in the previous case. We have not changed the Zi's, right? And but because of the property of the case, Y also must be adjacent to U, right? Because we said that every vertex in any minimum separating set is also adjacent to U. So therefore, there must be an edge from Y to U also, right? Now this contradicts the fact that P was a shortest UV path, right? Because we said that we started with the shortest UV path, which means that we go from U to X to Y to V was of the shortest length. But now if Y is adjacent to U, I can actually go from U to Y and then continue this path, which gives me even smaller paths. But by assumption, this was P was the shortest path, right? So this is a contradiction, and therefore we cannot have a separating set of size K minus 1 in this case. Right? So in G minus XY cannot have a separating set of size K minus 1. So, but G minus xy has a separating set of size k only, right? So, every separating set in G minus xy has cardinality k. But what we achieved by doing this is that we got a graph with smaller size, right? Because G minus xy has strictly less number of edges. And therefore, we can assume induction, right? So, by induction hypothesis, this graph G minus xy, right? G minus xy has k internally vertex disjoint, right? Paths from U to V, right? But all these paths are internally vertex disjoint paths in the graph G, because xy is an edge, whether I can choose to put in the path or not, right? I can just throw it away, right? So all the paths in G minus xy are also paths in G. Therefore, by induction I get k internally vertex disjoint paths in the graph G minus xy, and therefore in the graph G. So case 1 and case 2 are done, right? So then all it remains is our case 3. And since we already assumed that, right, case 1 and case 2 are not there, right? So we can assume that you cannot find a separating set which is having a vertex which is adjacent to U and V, and you cannot find a separating set, right? I mean, you don't have the property that every separating set has either, every vertex is adjacent to adjacent to U or adjacent to V, right? So that is not the case. Because these two cases are not there, we will assume the following. Okay? So therefore, we can find at least one, right? At least one minimum UV separating set, let us say W, such that no vertex of W is adjacent to both U and V, right? Right? That is the first case, right? First case does not happen, because in that case we will apply the first case, right? And W has at least one vertex not adjacent to U, right? Because if every vertex of W is adjacent to U, then again, right? Right. So it will fall into the first case. If every separating set has this property, but because at least one separating set does not have that property, we can say that there is some W where at least one vertex not adjacent to U, and at least one vertex which is not adjacent to V, right? So which means that we are in a case like this, right? So we have U and V, and W is a minimum UV separating set, and at least one vertex in W, right, is not adjacent to U, and at least one vertex in W is not adjacent to V, right? Now, so we are in the third case 3, right? Now suppose this is the case, right? So suppose if this is the case, let us list our separating matrices. Let's say W1 to Wk, right? Now W1 to Wk are our separating vertices, right? So these are the separating vertices. What I am going to do is the following, okay? So since W is separating set, every path from U to V must cross W, right? I cannot go from U to V without using some vertex of W, right? So I am going to define a subgraph by starting from the vertex U, traveling paths and going through the vertices of W, right? And the first time I hit a vertex in W in a path, I just stop and mark that path, right? Add that path. Then I look at another path, right? So I look at all the paths from U, which starts in U and ends in W, where I stop the path the first time I cross W. I don't want to go, further, right? After I reach W, I don't want to go any further. So every path it starts from U and reaches W for the first time, right? All such paths I take. So this forms a subgraph of the graph G, right? So all the U to W paths, right? U starting from U and ending in W, where I don't repeat vertices of W. I take this subgraph and then I add a new vertex called V dash. what I do is that I make V dash adjacent to exactly all the vertices of W, W1 to WK. So V dash is adjacent to W1 to WK. So I take this subgraph U to W paths, right, together with this new vertex that I am going to add. That I call the graph GU. Okay, GU is not a subgraph of graph, but it is a graph obtained by adding V dash to the subgraph of G, right, by the following. Similarly, I look at all the paths starting from W's, right, W1, W2, etc., and going to V, right, without repeating the vertices of W. Okay, so all the paths starting from here and going to V, right, or I can just look at the path from V to W without repeating W. So collect all such WV paths, and that subgraph together with the new vertex U dash, okay, U dash which is adjacent to all the vertices of W, W1 to WK. This defines the new graph GV. So I have the graph GU and I have the graph GV. Now the interesting property of GU, right, is that the number of edges in GU is strictly less than the number of edges in G, right? Because, we assume that there is at least one vertex from some vertex, the path from some vertex to V. So therefore, this, right, because this vertex, this vertex is not adjacent to V, you need to take at least two edges to go here, right? So if, in this graph, I have added exactly K edges from V dash to W. But here I have at least K plus 1 edges, right? Because V to every W there is a connection. And at least one is not a direct edge. So therefore I need at least K plus 1. So the number of edges in this graph is strictly less than the number of edges in this graph. But of course W is a UV separating set, right? Minimum UV separating set, because we did not remove anything in this part. And to separate W, I need to remove each of them, because I can, if I reach any of the vertices in W, I can go to V dash. So U V dash separator, W is a minimum separator for GU, right? But now for a smaller graph, right, of cardinality strictly less than M, right? Cardinality of GU is strictly less than M, I can use induction, right? Using induction, I can find K internally vertex disjoint U V dash paths in the graph GU. Similarly, I can find K internally vertex disjoint U dash V paths in the graph GV, right? So I have K U dash V paths which are internally vertex disjoint, and I have K U V dash paths which are also internally vertex disjoint. Now it is just a matter of observing, right, that if there are such paths, those paths must use precisely one vertex of W each, because there are K such vertices, right, in this graph, right, one vertex of W. So these edges must be precisely the edges used to define this K path, because there are only K edges here, and each of them has to be used exactly once. So therefore, what we get is K IVD path, right? So there is a path from W1, so W1 to V, right? W2 to V, right? W K to V, right? So these paths are in GV, right? Similarly, I have a U to W1 paths, right? U to WK paths, right? Because these paths must be going through U to W1 and to V dash, U to W2 and V dash, U to WK and V dash, right? U dash to W1 and V, etc. So, but now this part is, right? These parts are all internally vertex disjoint. Similarly, these paths are also internally vertex disjoint, right? So what I do is that I take the U to W1 paths and join with the W1 to V paths, right? So U to W1 path in the graph C, and in this If from this part I take the W1 to V paths, right? Now that cannot be intersecting U to W2 paths and W2 to this path because because we were very careful in selecting the subgraph from U to V that we don't repeat the vertices of W. So therefore, once I reach W, right, from here to here, there is no vertex or edge which is used around this part, right? So these parts of the graphs are basically disjoint except for the vertices W, right? So I get internally vertices join pass U to V through W1 through W2 through WK. So I have I have constructed K paths from U to V in the graph, which are all internally vertices join. So that is the proof of case 3, and therefore we finish all the cases. Okay. So GU is the graph obtained by looking at all the UW paths terminating at the first hit of WI and adding a new vertex V dash adjacent to VI. That is the case I am just describing in words. Similarly, GV is obtained by all WIV paths using at most one vertex of WI and adding U dash adjacent to each of the WIs, right? And since sizes of these graphs GU and GV, there is no dash, I think, right? GU and GV are strictly less than M, right? Yeah, strictly less than M. Using induction hypothesis, we have K internally vertices join U V dash paths in GU and K internally vertices join U dash V paths in GV. By the construction of these graphs GU and GV, right? Each such path in GU is a WI path and a WI V dash path. WI V dash H, right? And similarly, in GV, we have this case, and combining these paths, you get internally vertices join paths in the graph. So that is Menger's theorem. So what we have proved is that if U and V are non-adjacent vertices in the graph G, then the minimum number of vertices that can separate U and V, right, is equal to the maximum number of internally disjoint U to V paths in the graph G. Okay, this is a very, very important theorem, and we will use it now to prove some other results. Okay, some other important theorems.